Reinforcement learning is the paradigm of solving sequential decision-making problems. You can think about an agent, observe the state of the environment, decides what action is best to do, select it, observe the next state of the environment, select the next action, and so on, right? So generally speaking, RL is divided into two broad concepts or two broad subsets, prediction and control. And to see the difference between the two, prediction is the problem of finding the value of each state or each action in terms of the future consequences. And control is basically to find the best action at the current state based on its value, basically the action that gives you the maximum value over time. So both of these problems are quite relevant in healthcare. As you can imagine, medicine is all about sequential decision-making and prediction.
Standard reinforcement learning algorithms develop optimal strategies by interacting directly with their environment. Offline reinforcement learning, a sub-area of this field, takes fixed or previously collected data and uses the sequences of observations and decisions that are recorded in order to develop an understanding of the task, as well as try to formulate some optimal strategy. When data is limited, however, these optimal strategies are infeasible because there's no guarantee of convergence to those optimal decisions. So instead of trying to determine what is best in any given situation, maybe we can take an alternative view and try to learn what to avoid using these sequences of observations and decisions.
A dead end or a medical dead end is a state from which negative outcomes are inescapable. So of course, we want to prevent entering all the dead ends. As a result, we can use our prediction of a state being a dead end as a measure to call for an emergency when the patient becomes high risk, for example. In addition to that, we can double check the quality of possible actions or possible treatments by looking at how likely they may lead the patient to go to a dead end. And basically, we use this condition as the basis for proposing what treatments must be avoided, which shapes the pipeline of our methodology.
So as Mehdi introduced, by estimating dead ends and the value of the decisions that may cause a dead end to occur, we can alert a human decision maker of when a set of decisions are potentially high risk and may cause a patient in a healthcare scenario to enter these irrecoverably negative outcomes. If we can help the doctors in this way, we can help them then focus on treatments and decisions that are going to ultimately help their patients' health improve. Yeah, I'll take this as a start. So DED is an abbreviation for what we are calling dead-end discovery, which is an estimation procedure to try to identify when certain decisions may lead to dead ends. And the way that we approach or we formulate DED is that we want to estimate the likelihood that a decision would approach a dead end, as well as alternatively and independently estimate the effect that that decision may have on eventual recovery. So that if we are reducing eventual recovery, that will help confirm some estimate of whether or not a treatment will determine or will cause a dead end.
Yeah. To complement that explanation, I will also add that DD has two parts. One is to estimate if the current condition of a patient is very high risk, so that we can, for example, call for an emergency. And the second part is to analyze the quality of each of the treatments. And if they're not secure enough, we can still tell the doctors that these treatments are not good, so that it shrinks the scope of the possible treatments and makes the intervention easier and more secure for doctors.
I think the fact that dead-end discovery uses two different views, right? A view of the probability of survival or recovery, and then another view of the probability of non-recovery. Like looking at these two dueling networks to inform its understanding of what treatments maybe should be off the table is also very novel. And it's part of the reason we're very comfortable with saying this would be a reasonable option for somebody to look at and then reduce the space of treatments that they consider.
Yeah, first of all, we can show that our DD method requires exponentially less data compared to standard R solutions, which try to find best treatments. To see that intuitively, we can observe that our paradigm doesn't need all of the possible alternatives to come up with the solution, because DD doesn't suggest the best treatment. In addition to that, we can also show that in most cases, the worst thing that can happen is that our pipeline remains silent because, for example, it doesn't have enough training data. And what happens in those cases is that the DD method simply places decision-making fully back to the hand of the human clinicians. At the end, I would also to emphasize that our method doesn't replace the doctors. Rather, by definition, it kind of extends their capacity to avoid insecure treatments.
There are many clinical conditions other than sepsis that you could imagine this analysis being applied to. We don't always have to be in the intensive care unit or severely sick to want to act in ways that we've seen clinicians act previously. You could also imagine using the dead-end analysis to study the impact of other measures. For example, maybe we want to look at demographic information and variation in how we predict things other than accuracy. And then finally, we could imagine some other non-medical setting where it's important to act as other humans have in the past. We don't want to do something completely novel. In financial markets, maybe we want to stick closer to what we've observed other people doing in the past.